Okay, we'll get started here in just a minute or two, continuing on where we left off last time, which I think is chapter 15. So again, we'll start up here in just a second. I think this is about where we left off in terms of chapter 15. Like usual, if you have questions, feel free to type them in and we'll get to them obviously as we go through. All right, so last time we started talking about KSP, KSP, which is essentially a equilibrium constant. KSP is essentially used for things that are typically thought of as being insoluble. So typically when we deal with KSP, it's usually just our products. As when we look at the reaction that's usually involved with KSP, like I said, it's usually for those insoluble type guys. So for example, like silver chloride, when it breaks apart into a silver ion and a chloride ion, again, when we would do our KSP expression, it would just be our products in most cases, as that is typically how they're arranged. Solid on the left-hand side of the arrow goes to our aqueous ions on the other side of the arrow. And thus, when we do our KSP, it is typically only the products that are involved. Because these things are typically insoluble as well, that usually means, as we saw last time, that our KSP values are usually very small values. And that means obviously like a normal K value, that if you have a small value, you mainly have reactants at equilibrium. And that's what it means here as well. So, you know, for the most part, these things are insoluble. But as I also mentioned last time, even though something is technically insoluble in terms of, say, solubility rules and things of that nature, everything has some degree of solubility. So even if it's a very, very minuscule amount, it will still be able to really set up this sort of equilibrium that we see up on top there. But again, it just may mean that the ions, the silver and the chloride, for example, is a very, 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 very small amount. So small that it is normally considered, based like on the solubility rules, as being insoluble, that it really doesn't dissolve. But there is some level of things being able to sort of dissolve. So we talked about calculating KSP. If you need to calculate the KSP, you essentially just need to figure out the concentration of the ions at equilibrium. And once you calculate the concentration of the ions at equilibrium, you put it into the KSP expression, and that would give you your KSP. We also saw that if you're given sort of a KSP and you want to figure out the solubility, which usually is either molar solubility or solubility in terms of grams per liter, you typically do need to sort of do an ice table in that case. The ice table is similar to ones we've done before, except that typically people use S instead of X, and that stands for the molar solubility. So ice tables, very similar to all the ice tables we sort of done before. You would solve for S, but again, when we do solve for S, again, is typically the molar solubility, which is moles per liter, which again, as we did a couple of problems last time, if you're looking for the grams per liter, you would then need to use the molar mass to figure out how many grams per liter you could dissolve, for example. So we sort of finished up talking about the idea that there are things that do affect sort of the solubility of substances. The one that we finished up on last time was the common ion. So a common ion will basically suppress a solid from dissolving. And if you just look at sort of the way that the equation is sort of set up, solid to aqueous, if we have a common ion, that would be like adding more guys on the right-hand side, which means it should shift the equilibrium to the left-hand side and keep that solid sort of from dissolving. So the presence of a common ion in terms of solubility will actually decrease the solubility of a particular substance. Any questions on any of that stuff that we talked about last time? So we're now going to actually look at another sort of factor that affects solubility, and that's actually pH. So pH and solubility are tied together, especially when we're dealing with things that are sort of acids or bases and sort of their solubility in terms of they will dissolve or not. The presence of a common ion, as we saw earlier, did decrease the solubility. Now we do have insoluble bases, and insoluble bases will start to dissolve in acidic solutions, while if you have an insoluble acid, it would dissolve in basic solutions. So to sort of illustrate this, if we look at what we got going on here in terms of this equilibrium here, which is our magnesium hydroxide, obviously a insoluble base. And it will set up this sort of equilibrium, which we could write our KSP expression as we do see down here on the left there. The KSP equals the magnesium ions times the hydroxide ions squared equals 1.2 times 10 to the minus 11. And we can figure out sort of the solubility by doing a problem like we've done earlier. If we take our magnesium hydroxide and our magnesium ion plus our two hydroxides. And if we did sort of our ice table here, this again would be 0, 0, just to refresh you on that. This would again be plus S and plus 2S. Remember, again, taking the coefficient into account, which means at equilibrium, we have S and 2S. This would go into our KSP expression, much like we did in some problems earlier. This would give us S times 2S. We also still need to square it because of the square here. And that is going to equal our 1.2 times 10 to the minus 11. And if we do that, again, you want to always make sure you square not only the letter, but also the number there. So that should give us 4s cubed equals 1.2 times 10 to the minus 11. We're going to divide by 4 and take the cube root of that. And we will get something like S is equal to 1.44 times 10 to the minus 4. Any questions first on that calculation? Again, that's very similar to the calculations that we have done before. Now, in terms of pH, right, in this sort of equilibrium, it is the hydroxide that's important. And in terms of the hydroxide concentration, we could see from the table that it's actually equal to 2 times S. So to find the hydroxide concentration, we would need to take 2 times 1.44 times 10 to the minus 4. And if we do that, we end up with 2.88 to the minus 4 molar. And again, because that's hydroxide, it won't let us get the pH right away, but we can get the POH, which if we put that in, that's going to give us a POH of 3.54. And thus, this will give us a pH if we take 14 minus that. And we will end up at 10.46. So a couple of things about what we've sort of done up until this point. Here we have a KSP equilibrium because it does involve hydroxide, or if it would involve obviously H plus, if it was more of an acid. We're able to use our KSP table to figure out the hydroxide concentration at equilibrium, which would allow us to figure out that this solution's sort of baseline pH at this point is 10.46. So the baseline pH here of this solution, when you make it or have it in solution, would be a pH of 10.46. So we could see what will happen perhaps if we adjust the pH. Let's say what happens if we are at a pH that is, I'll just write it here since I overwrote. So let's say what happens if we take the pH of that solution and we essentially drop it less than a pH of 10.46. So if we take this solution and we lower the pH to less than 10.46, what's going to happen is this. In order to lower the pH to less than 10.46, we need to make it more acidic, which means we need to increase the amount of H plus. And if we increase the amount of H plus in this case, what's going to happen is H plus is not part of the equilibrium, but H plus and OH minus do react together to make water. Yeah. So essentially what we would be doing if we lower the pH less than 10.46 in this case is we would be removing OH minus to make water, basically. Water being a liquid, obviously it's like taking the OH minus out. And by removing the OH minus, that should cause the equilibrium to shift to the right, and it should become more soluble, right? In that case, as we will get more of the solid to basically dissolve in that case. And that's what it means by insoluble bases, which is what this is soluble in acidic solutions, because when we drop the pH, we add more H plus, the H plus removes the hydroxide, causing the equilibrium to shift to the right and making more of that solid start to dissolve. Now, if we did the opposite and we decided, hey, we're going to bring the pH above 10.46, so if we go above pH of 10.46, when we do that, again, the only way really to bring it sort of above in terms of 10.46 or raise the pH is the OH minus concentration should be going up. Yeah. So we should be increasing the OH minus concentration. And that means when we look at our equilibrium, that would be like adding more OH minus, right? So it'd be like adding more OH minus. That is going to cause the equilibrium actually to shift to the left, and it will become less soluble in that case. So the pH of a solution is sort of really important as well in terms of the solubility, or even the ability to make something that is technically insoluble more soluble. And it has to do with obviously the presence, when we talk about insoluble bases or insoluble acids, the presence of OH minus and H plus. Obviously, increasing the H plus concentration there in a base will make it more soluble, and decreasing the H plus or increasing the OH minus concentration will make it less soluble. Opposite is sort of true if you're talking more about an insoluble acid, which I'll just kind of sketch it here. So if we're talking more of an acid, right, what that would mean is on the product side, you have some H plus. And in that case, if you made it more basic, right, the OH minus and the H plus would come together to make water in a more basic solution, and thus shift it to the right and make it more soluble. And again, that's what it means when we talk about insoluble acids will dissolve in basic solutions, and vice versa. If we made it more acidic in an acidic insoluble acid, we would be adding more H plus. If again we wanted acidic on that, and it would shift it that way. So sort of opposite, obviously, the effect that you would have with a base, like we did diagram there, but the acid would sort of work the same way based on, obviously, the same sort of principle, which is really still Le Chatelier's principle of either adding or removing something from this equilibrium. Any questions on how to calculate the pH of a solution from the KSP, the effect of acid or bases on pH? Okay. All right. So another thing that we oftentimes use sort of KSP to help us with is to decide whether or not, again, we would expect a precipitate to happen. So we've talked now about sort of common ion as affecting solubility. We talked about pH as affecting solubility. There's also sort of a third idea here that can affect the solubility. And as we will see, it is basically concentration. So you do need the concentration of everybody to be sort of correct to either see a solid form or maybe not see a solid form. And we can use Q to help us decide that. So again, we talked a little bit about this earlier. We could use Q if it's greater than the KSP, then we would expect a precipitate to form. If Q is less than the KSP, then we would expect no precipitation to form. A reminder that Q is the same thing that we've seen before many times. It is basically calculated the exact same way as the KSP. The only difference is here we're using it to compare to the KSP. So it's kind of like initial conditions, seeing if a precipitate would dissolve. So let's take a look at sort of this guy here and this problem. So if we mixed 2 milliliters of 0.2 molar sodium hydroxide and we mix it with 1 liter of calcium chloride, will a precipitate form? So really the first thing you want to sort of think about is sort of those solubility rules. Is there really any combination? And the combination really is going to be a double displacement sort of reaction. So is there any combination which when these two guys come together, or really these two guys come together, will there be a solid that's formed? So again, if you are so familiar with your solubility rules, it'll be helpful, obviously, to know some of those things. But if you look at the KSP table, you could probably see a KSP value for calcium hydroxide, which would imply that that could make a solid, obviously. So what we need to figure out is Q greater than the KSP for calcium hydroxide? So when calcium hydroxide, which is our only possible solid in this case, when it breaks apart, it does break apart into a calcium ion plus 2 hydroxide ions. And we could write our Q for this, which is our product, which is our calcium, times our hydroxide, and we do need to square it. Now, when we go into this, we do need the concentrations of these guys in the solution when they're mixed together. So it's kind of like a dilution problem, M1V1 equals M2V2. So for example, for our hydroxide, the only source of hydroxide is going to come from our sodium hydroxide, which is 0.2. And in this case, we would have 2 milliliters times our 0.2 molar. Now our total volume in this case, and again, you could do it a couple different ways, but our total volume is 2 milliliters, right, from our sodium hydroxide. We're going to mix it with 1 liter of calcium chloride. So just to put them in the same units, I'm going to do that as 1,000 milliliters, which is the same, obviously, as a liter. You could convert the 2 milliliters into, 0.002 liters if you want. But basically, just kind of keep it a little bit easier, I think, 1,002 milliliters. Again, the milliliters will cancel. That's going to leave us with molarity, and we would get 2 times 0.2 divided by 1,002. 2 there. And we'll get something like 3.99 times 10 to the minus 4 molar. Now our calcium ion, the only source of calcium will come from the calcium chloride. But again, we need the concentration of calcium, not from that, but in the mixture when they come together. So we would do the same thing for our calcium. We're going to take 1,000 milliliters. Again, I converted the liters into milliliters times our 0.1 molar. Again, divided by our total volume, which in this case, again, I converted to milliliters. The milliliters cancel, leaves us with molarity. That gives us 1,000 times 0.1 divided by 1,002. And that gives us 9.98 times 10 to the minus 2 molar. So any questions on where those numbers came from? So again, here we just want to make sure that we get the concentrations in the actual mixture together, because that's kind of the whole purpose of this. So at this point, we have the concentrations of these guys when they're mixed. So we'll put this into our Q expression. And 3.99 times 10 to the minus 4, we're going to square it. And if we do that, gives us something like 1.6 times 10 to the minus 8 as our Q value. And at this point, we want to take our Q value and the KSP value, which again, if it's not given to you, you may have to look up on a table. And we want to compare the two. And what we see in this case is Q is less than the KSP. And that means that it will shift to the right, very badly drawn there, and to the right again in all of these sort of KSP situations. The right-hand side is aqueous ions, which means in this case, we should expect no precipitate to form in this case. Even though solubility rules may tell you that when you put calcium and hydroxide together, you should get a solid. This explains, again, another important aspect of solubility, which is concentrations. Again, in order to see a solid actually form, you actually do need a minimum amount of concentration of each of those ions to come together to actually allow you to see the solid form. Any questions on any part of that there? So those are really three sort of aspects of solubility that we oftentimes don't think about, especially when we think about sort of those solubility rules. We sometimes think about the solubility rules as they're hard rules, no matter what the situation. If you put those things together, you know, you'll always see the solid or you won't see the solid, for example. But there are three sort of important factors that we just finished talking about. Again, the common ion, the pH, and then also the concentration. All these things sort of need to be right in order for something to be sort of insoluble and a solid being able to be seen. Any questions on that there? Okay. So then let's talk about another sort of helpful aspect of KSP. And this sort of idea here, this is something that really ties together with labs that, you know, we don't really do anymore here at this school. Other schools still do. There's a whole kind of part of this class that used to be done a lot, which is known as qualitative analysis. And qualitative analysis is basically a whole bunch of labs where you have a whole bunch of individual ions that are floating around in the solution. A lot of times they're cations. They could also be anions floating around the solution. And the idea behind sort of qualitative analysis is to sort of selectively precipitate out one ion at a time. And in order to sort of identify what ions are present, you sort of need to be able to just pluck out one sort of ion at a time and then do some more testing to verify that that ion was in the solution, while keeping pretty much all the other ions basically floating around in the solution. And you should be happy you don't have to do those experiments. They were horrible, but this was referred to really as selective precipitation. And that's really the idea here in this problem. So when we look at this problem, what we see is what is the concentration of silver that's required to precipitate silver bromide in a solution that contains both Br minus and Cl minus ions at a concentration of 0.02. So basically what we got is you have a solution and you have bromine ions floating around. You have chloride ions floating around, and they both have a concentration of 0.02 molar. And what we're trying to figure out is if we take some silver and we toss it in there, we know that if we do, based on solubility rules, the silver and the bromide will come together to make a solid, and the silver and the chloride will also come together to make the solid. The problem, though, is if you look at the picture on the right, those are the solids that they will make. So if you don't do this sort of correctly, what you'll get is a white solid from the silver bromide, you'll get a white solid for the silver chloride, and you can't, if you're trying to separate those out, go, I think this little white precipitate is the bromide, I think this white precipitate is the chloride, and you can't, one have no way to really know, what is what. So the idea here is we want to sort of selectively precipitate out one first versus the other. So in this case, we want to take the bromide out first while leaving the chloride still free to basically float around in that solution as an ion in an aqueous environment. So to do that, we could use our KSP to help us decide what we need to do. And it really does start with the KSP expression. So if we write the KSP expression for our silver bromide, it is going to be the silver ion times the bromide ion, and that's going to equal 7.7 times 10 to the minus 13. And what we're interested in is the silver concentration that we need. So we could rearrange this and solve for the silver concentration by taking the KSP value and dividing it by the bromide value. And in this particular case, we know that the bromide is 0.02. So we could simply put that into our expression here. And what we get when we do that is (3.9 times 10 to the minus 11). So let's talk about really what that number represents. That number represents that until I add silver into this beaker on the top right, until I hit a concentration of 3.9 times 10 to the minus 11 for the silver that's being added in there, I will not see anything precipitate. But as soon as my silver concentration gets to 3.9 times 10 to the minus 11, I should start to see my, silver bromide start to precipitate out. So as soon as I sort of hit a silver level at that concentration, that is when I should start to see, again, the bromide part coming out. So I will start to see some white solid being formed. I could continuously sort of add my silver above that concentration. We could also do the same calculation for our chloride. And our KSP for our silver chloride would be our silver times our chloride equals 1 times 6 to the minus 10. Same idea here. We're going to solve for the silver concentration that's needed to precipitate out our silver chloride by rearranging our KSP expression. And in this particular case, again, the chloride was also 0.02. So 1.6 times 10 to the minus 10 gives us over 0.02. Gives us a concentration for silver of 8 times 10 to the minus 9. So what does that number represent? That number represents the minimum amount of silver that's required to start to precipitate out our silver chloride. Let's call this guy silver chloride. So as soon as our silver concentration hits this number, we should start to see some silver chloride come out. And what we see here when we look at these two is if I want to precipitate out just the silver bromide in this case, and leave our silver chloride, our chloride actually, in the solution. We would need a silver concentration that's greater than 3.9 times 10 to the minus 11. But we need one that is less than 8.0 times 10 to the minus 9 molar. And what that will do is allow us to precipitate out the bromide and leave the chloride in the solution. Any questions on that? So what do these numbers sort of really mean if you were doing this? What it means is if you had that solution that had the bromide ions and the chloride ions in it, and you start adding silver to it, and your silver concentration has not hit 3.9 times 10 to the minus 11, you will not see any solid. Technically speaking, as soon as you hit a silver concentration of 3.9 times 10 to the minus 11, you will start to see some white solid come out. And you could feel pretty confident that that white solid should be the silver bromide. And you could continue to add silver and increase the concentration above 3.9 times 10 to the minus 11, as long as you keep it below 8 times 10 to the minus 9, and you'll continuously see white solid precipitate out. And all that white solid, as long as you keep it between those two numbers, should be silver bromide. In reality, at some point, you will probably stop seeing some white solid come out. And at that point, you could feel pretty confident that you have successfully precipitated out all of the bromide as silver bromide if you stop at some point seeing solid form. And if that should happen, at that point, if you want to then take out the chloride, you would then increase the silver concentration to 8 times 10 to the minus 9. You once again should start to see some white solid come out, which you, at that point, you should be fairly confident that the white solid coming out is the silver chloride. And you can continue increasing it above 8 times 10 to the minus 9 until you do not see any more white solid come out. And by doing that process, you have now selectively precipitated out each ion separately from each other. You can look at each of those white solids and be very confident that the first batch was the silver bromide that came out, and the second batch, after you sort of stop seeing the solid come out, would be silver chloride. Any questions on sort of using KSP to selectively sort of precipitate? There's also a reason why this question was worded the way it is, and it has to do with the idea of what we talked about last time as well. The question wants to know what you need to add to precipitate out the silver bromide first. The reason you could precipitate out the silver bromide first is this is a case where we can look at the KSP values and decide which one should precipitate out first. So for example, in each of these guys, they break apart into 2 ions, right? 2 ions there, 2 ions there. So because they do break apart into 2 ions each, we can look at the KSP values before we do any calculation, and we can decide that the silver bromide has a smaller KSP value, which means in this situation is going to be less soluble than the silver chloride, which has a larger KSP value. And that's why the question asked for you to precipitate out the silver bromide first. Any questions on any of that stuff that we just talked about? Okay. So this is just a table, not from your book, but I think you have a similar one. But this is typically what we what is known as qualitative analysis, which is really where we use sort of KSP and sort of that idea of selective precipitation. And it's really a long group of experiments. There's actually 5 or 4 different sort of groups. And there's groups of ions. They're not related to each other from the periodic table, but they're related to each other based on solubility properties. So for example, that is our guys that are insoluble in chlorides, bromides, and iodides, are silver, mercury 1, and lead, which is our group 1. And we use a reagent to precipitate those out. So for example, hydrochloric acid is a reagent that will precipitate those guys out. They come out as chlorides. And again, you can kind of do a lot of selective precipitation to select each of those ions individually. And then there's a lot of really specified or specific tests that allows you to identify each ion by a specific test at the end. So this is a very common sort of groups of experiments that are done a lot in actually, like 51 class, second semester. And it's really all about selective precipitation. There's what's referred to as a group reagent, which HCl is. Hydrogen sulfide is a group reagent for group 2, also for group 3 as well. And, you get some sulfides and hydroxides sort of precipitates. And group 4 or group 5 is really these guys down here. And those are guys based on solubility, potassium, sodium, ammonium. If you remember solubility rules, those are things that are soluble in everything. So we usually save those guys in this sort of experiment to the end, because they should be the only things that are left, because you can't really add anything to precipitate those guys out. So they do remain in solution for a long period of time. Any questions on KSP or anything like that? All right, so then we're going to talk about complex ion and complex ion equilibrium. So we're going to add another sort of K to the mix. All right, so complex ion is basically a metal, and usually it's a metal that has a larger positive charge, like +2, +3 type of charge. And it has a bunch of molecules or ions attached to it. And these are what are referred to as ligands. And ligands are usually Lewis bases. So we talked about Lewis bases. And if you remember, Lewis bases are electron pair donors. So they donate an electron pair. So things that have a negative charge are really good. That means they have extra electrons. Polar guys with non-bonding electrons on it, like water, like ammonia, these are good Lewis bases. And so if we look at this formation, we have a metal. We have our Cl minus, which is our ligands. They're going to come together, and basically this metal is going to be attached to all 4 of those guys, and we will get an overall -2 charge. We could write a K expression for this, which we'll add to our ever-growing list of Ks. This is Kf, which is known as the formation constant, and it is the equilibrium constant for complex ion formation. It is like every other equilibrium constant that we see. It is our products over our reactants. And just like normal, any type of coefficient, like we have here, will also obviously show up here as well. Now, when we have a large Kf value, that means that the complex ion is more stable. And that means, again, basically a large K value means we have more products. And in this situation, when we talk about this type of equilibrium, it is aqueous ions goes to complex ion. Yeah. So again, a large K value would put us over here on the right-hand side, and we would have a lot more of a complex ion there at equilibrium. Now, depending on sort of your ligand, as you can see on the left there, will give it sort of different properties. So cobalt with water surrounded by it, which is essentially what it means when we write aqueous next to cobalt. Has more of a blue tinge. If we kind of substitute out those waters for chloride, we will end up with something with a bluish sort of tinge to it. Now, these ligands, they do come on basically one at a time. So they do happen one at a time. So for example, if we look at the one that we were just looking at, we had our cobalt plus. The first thing that would happen is we would form this first guy that would come on. And we would get something like COCl plus. Then what would happen is that COCl plus would pick up the next one. And we would get COCl2. Then our COCl2 would pick up the third one. And we would get COCl3. And our last guy here would pick up the fourth one. And we would get our final complex ion, which is our COCl4 2-. Now, a lot of times we look at sort of the overall reaction, but these are sort of a stepwise addition of these ligands. And each of these are actually equilibrium, which means for each of these steps, you could potentially have a K value for each of these steps. And if we were to add all of these steps together, we would do like we normally do. Anything that's on opposite sides of the arrow, that's the same, would cancel out. So in this particular case, if we went through, this guy would cancel, this guy would cancel, this guy would cancel. And that's really how we get to our overall reaction that we saw on the previous page, where we have our cobalt plus our 1, 2, 3, 4 chlorides makes our complex ion. Right. And if we weren't given the KF but wanted to figure it out, just like we talked about with equilibrium, the KF in this case would be all of those guys multiplied together, right? So just like we talked with regular equilibrium, if you add a bunch of reactions together, you multiply the K values together. And in some of these sort of KF problems, you may have to do that. You may have to kind of combo some reactions together and get an overall K value, again, by multiplying them. Any questions on that there? Now, again, like I said, very common ligands. We'll talk about in a later chapter as well. Water, which again has those non-bonding electrons on the oxygen and it's polar. NH3, same deal, non-bonding electrons on the nitrogen and it's polar. Cl minus, Cn minus, again, there are minuses, so they actually gain some electrons along the way, which means they have extra electrons to donate. Another thing that we sometimes talk about in terms of complex ions is what is known as coordination number. Coordination number is how many atoms are directly bound to the metal. So when we take something like cobalt with our 6 waters attached, it has a coordination number of 6. Essentially what that means is, again, we have our cobalt and directly attached to it really is our 6 waters. We're going to run out of room, so I'll just write it like this. 1, 2, 3, 4, 5, and one more. But basically, directly attached to the cobalt in this case is the 6 oxygens, and that gives it a coordination number of 6. Here with the chloride, there's 4 chlorides attached to the cobalt, so it has a coordination number of 4. Sometimes, though, people think the coordination number will always be this number, and it won't. There are ligands which are known as being monodentate, as we'll talk about, which means they attach in one place. There are some that are referred to as being bidentate, which means they attach actually in 2 places. So for example, if I had, say, a metal that had C2O4 attached to it and 2 of them, in this particular case, this is oxalate. And if you draw oxalate, it will look like this. And for every oxalate, and we'll put our metal in the middle, each of these oxygens will actually bind in. And you would obviously have the same deal going the other way. where this guy would have two guys binding in. So when oxalate binds, although there's only two oxalates, every one could do two bindings. So it actually would have a coordination number of 4. So we'll get more into that. It's not always going to be obviously equal to this number here, as we'll see in a later chapter, but it will be if it's monodentate. But that's actually going to be covered in a little bit later of a chapter. But just to give you a heads up, it's not always this number on the bottom for the coordination number. All right. So let's take a look at a problem that involves KF, and we sometimes will deal with these guys a little bit different than how we typically will deal with normal sort of ice tables. You typically do have to do an ice table here to sort of solve a lot of these questions. So if we take 0.2 moles of copper 2 sulfate and we mix it with a liter of 1.2 molar ammonia, what is the concentration of copper at equilibrium? Just to make everything easy in this particular problem here, we're going to assume that all the volumes basically remain as 1 liter. So let's just make the math a little bit easier. And let's sort of go through this and show you how you sort of do this type of problem. So the first thing that you would want is the concentration of each of these guys in the solution. And again, we're just going to assume everything is 1 liter. So that makes the math easy. So initially here, we'll have 0.2 molar. For our ammonia, we'll have 1.2 molar, and we would have 0 here. Now, when we do this type of problem, there's a couple of things that's important. And typically when we look at the K value here, for our KF values, they are typically very large values, yeah? Which 10 to the 13th is obviously a very large value. 10 to the 13th essentially means it's a pretty safe assumption. We're all heading this way. And that actually is an assumption that we do when we do these type of problems. We assume that because the K value is so large that all of the metal will end up in the complex ion. And what that means is when we get to the change part, we actually do know what the change is going to be. It's going to be the metal. So here, this would be minus 0.2. This would be, I'm just going to kind of combo everything together, 1.2, which is our initial, minus, we still have to multiply it by 4, times 0.2, and this would be plus 0.2. I need the parentheses there, but I put it in for free. So this is equivalent to where we would normally do sort of this ice table. If we had 0.2, we had 1.2, and we had 0. We would normally do minus x, right? We would do minus 4x, and we would do plus x. And then we normally would come to equilibrium and have 0.2 minus x, 1.2 minus 4x, and x. So what I did actually here is what we normally would have at equilibrium here, except in this case that we actually know what x is. So in this case, x is going to be our copper concentration, right? So that's sort of the slight difference is we sort of combo a couple of steps here, which again is equivalent to doing a normal ice table like we would do over there. Which means at equilibrium, we will have nothing of the copper left. We will have 1.2 minus 4 times 0.2 gives us 0.4. And here we would have 0.2. Any questions on the table? So a little slightly different. We make that assumption that all of the metal should be tied up in the complex ion. So we use the metal as the change. And we also, again, just kind of put the concentration in and then also use the numbers here to get numbers at equilibrium. Any questions up until that point? Now, you may be saying to yourself, the question wanted to know, what is the copper concentration at equilibrium? Yeah, so you do. So, and this is typically the case. We're going to see a table in just a second of KF values, but pretty much all KF values are very, very large. And this is typically where we do make this assumption is when we're dealing with complex ions and we're dealing with KFs, because those KF values are typically very large. This is really the only place where we can make this assumption. It's kind of like the opposite assumption that we do when we do like x is equal to 0 with a very small k value. So this is sort of the opposite here, but it's really almost only happens with this type of equilibrium when we're dealing with complex ions and kf values. Other questions? So obviously, this wouldn't be much of a problem if 0 was our answer. So there is a sort of a second assumption that we do with these complex ion problems is, although we assume that pretty much all of our copper in this case is going to be tied up in that complex ion, it is still an equilibrium, which means even though it's pretty much all going to the right, there's still a little bit of this guy that wants to go back to the left. And the second assumption that we assume here is that although it mostly gets used up, the metal ion, some will come back the other way. But at equilibrium, it should be very small. So you should have a very small amount of free metal ion at equilibrium. So you should have a very small amount of free metal ion at equilibrium. So the way that we could figure it out is actually here use our equilibrium expression. So if we write the Kf for this case, it would be our products, which is our complex ion, divided by our reactants, which is our copper, and our NH4, which we still have to take to the 4th power, again, because of the coefficient. So although we zeroed out here, we then will go back and call our metal ion X so we can solve for it, because now we have this number, we have this number, and we have this number from the table, which are right here. And we could solve for the copper concentration. So if we put our numbers in, we see that it is 5.0 times 10 to the 13 would equal our complex ion at equilibrium, which is 0.2 from the table above, which is why you need to do that table. Gives you your copper ion concentration and our NH3 also from the table above. So basically what happens is these two guys switch places and we get that the copper concentration equals 0.2 divided by our Kf value times our 0.4 to the 4th. And if we do that, what we will end up with (1.6 times 10 to the minus 13 molar. And this number is super small, which basically justifies our second assumption that, and really our first assumption as well, that pretty much all of that copper 2 ended up in that complex ion. Only like 1.6 times 10 to the minus 13, which is pretty much nothing, is coming back the other way. But there's still, technically speaking, if you go out like 12 decimal places or 13 decimal places, there technically is a little bit of it coming back, which is almost pretty much thought of as none. And that's why we usually will see, and what you usually will see is if you have a situation where we want to make a complex ion, that is definitely favored because of these large values of K. Any questions on how to work through this type of problem here? All right, so why don't you take 5 minutes or so, start working on this one, and then we'll go through it and see how it's a little bit different than maybe the other one, but kind of similar. So work through it kind of the same way. We pretty much want to know everybody's concentration here at equilibrium. If we mix together 150 milliliters of 1 times 10 to minus 3 molar silver nitrate with 200 milliliters of 5 molar Na2S2O3. Take about 5 minutes, get started on it, and then we'll come in and see how you're doing. In this case, you have a stepwise equilibrium with an equilibrium constant for each one. And again, there's a couple different ways you can solve it, but why don't you get started and see how you do, and then we'll talk about it. If you have questions, feel free to ask. Okay, so hopefully you got a little bit of a jump on this. So let's just kind of see how everybody's doing. So a couple of things here. Again, this one is more of a stepwise equilibrium formation of our complex ion, and we'll deal with that in just a second. But let us take a look at a couple of things. We pretty much want to find the concentration of pretty much everybody there at equilibrium. And we do need to figure out basically the source of silver and the source of the S2032 minus. The source of the silver in this case is going to come from the silver nitrate. So we do want the silver concentration. Remember though, when you do these, you want the concentration of these guys in sort of, excuse me, the mixture. So we are mixing 150 milliliters plus 200 milliliters, which gives us a total volume of 350 milliliters. So again, you can kind of use M1V1 equals M2V2 here. So our silver nitrate would be 150 milliliters. We're going to use a molarity of 1.10 to the minus 3. We're going to divide it by our total volume of 350 milliliters. Again, the milliliters are going to cancel. So really when we mix this together, our silver concentration is something like 4.29 times 10 to the minus 4 molar. We would also want our S2O3, which would come from our sodium thiosulfate. And we would take the same sort of calculation, our S2O3 2 minus. We're going to use 200 milliliters of it. And its concentration is 5 molar. Again, divided by the total volume here of our mixture, which is 350 milliliters. And that will get us a 2.86 molar for that guy. Any questions on that so far? Just getting the concentrations. So again, usually when you do sort of KF type of tables, ice tables, even though we're mixing and all that, we sort of do it in molarity after everything's been mixed. We sort of want to get the molarity of all of our guys after that mixture has sort of come together. All right. So we're going to use those and our stepwise sort of guys over here. And what we could do is essentially add both of these reactions together. And if we add both of these reactions together, so I'm just going to kind of do it down here. This will cancel. And that's about it. That will cancel. So I'm going to write the combo formula there. We would have our silver plus our 2 thiosulfates going to form our complex ion here. And again, this is what you get when you add both of those formulas together. And if we want the KF for this, we would take basically K1 down there times K2 because we added them together. And if you do that, just to save room, I'm not going to rewrite those numbers, but if you multiply them together, you would get something like this, which technically would be our KF of 2.9 times 10 to the 13. Any questions on those steps so far? So again, we figured out the concentrations of our silver and our S2O3 2 minus. We added both of those reactions together to give us really the overall reaction. And again, since we added those together, they both have K values. When you add them together, you multiply the K values. Again, not add the K values. So now we can do pretty much our ice table like we did before. We will take our initial concentration of our silver, which was our 4.29 times 10 to the minus 4 from the previous page. And that's molarity. We have 2.86 here, molarity and 0. We could see, since we did calculate it, we do have that large value, right, for our KF. Yeah, so this is sort of an idea like you made this solution. So typically you would do this usually in molarity, like you poured it together, and then now that's sort of the initial concentration, everything. You want to see what happens. Sort of the slight difference in that is like in a titration, you're constantly adding volume. Or in like a buffer, if you have a buffer already made, you're adding more to it, maybe consistently to change the pH of that buffer. So those are two situations where we definitely would want to do it in moles because of that, because you're kind of consistently sort of adding. Here you can kind of think about it, you know, although you are adding these things together, what you're looking at is really the end result after everything was added together. And you want sort of the concentration of these ions in that sort of mixture together. So I would say with KF, do it in molarity. Just make sure you get the right molarity. And with the other ones, you want to definitely do it in moles and then convert it to molarity at the end. In reality, if you do this one in moles and sort of convert it to molarity at the end, you probably will be okay as well. But, you know, typically speaking, we just kind of go right to the molarity in these type of tables. Other questions? Okay, so since our KF is really large here, we're going to make the same assumption that in this case, all of our silver is going to get used up. So we're going to do that as the change. So we're going to do it similar to what we did before. We're going to go minus 4.29 times 10 to the minus 4. Here again, I'm going to combo these kind of steps. So 2.86 minus, don't want to forget the 2 times the 4.29 times 10 to the minus 4. Again, here the 2 from the coefficient here. So just like we talked about, that's the same as like 2x. And then this would be plus 4.29 times 10 to the minus 4, which means when we do reach equilibrium here, we will have 0 of the silver. For our S2O3 2 minus, we will end up with 2.86 essentially still. And we'll end up with 4.29 times 10 to the minus 4. So this table, very much like the last one that we did. And also from this table, we actually have two answers that we're looking for. We have the concentration of S2O3 2 minus is equal to 2.86 molar. We also have the concentration of our AG S2O3 3 minus is equal to 4.29 times 10 to the minus 4 molar. So if we look back at sort of our what we're looking for, we just figured out this concentration. We also have our S2O3 2 minus concentration as well. So we still have a couple more things that we're looking for in terms of concentrations. So this is where I mentioned earlier that there are a couple different ways that you could actually approach this problem. So I'm just going to do it one way, and then I'll sort of explain to you an alternative approach. When I go back to my stepwise equilibriums here, each of these are essentially equilibrium, basically steps, right? And they both have an equilibrium constant associated with it. And what we just found in that first table is the equilibrium concentrations of this guy and this guy, which if we just use K2 in this case, we can actually get the concentration of the AgS2O3 minus, which is also what we're looking for. So I'm going to do that first. So using K2 from below or from the problem, K2 would equal the products, which is this guy, divided by our reactants, which is this guy, which is one of the things we're looking for. And again, that would equal our K2 value there of 3.9 times 10 to the 4th. And again, I chose K2 because as you can see here, I pretty much have everything except for that one. So that would allow me to solve for the one that I'm looking for. And that would equal the concentration of our product there, 4.29 times 10 to the minus 4, divided by our 3.9 times 10 to the 4th, and our S2O3 2 minus, which was 2.86 So just to reiterate here where we just did there, basically to rearrange this guy and this guy just switch places. The values come from the table above that we got. So that's where all the values came from. And because we're doing not the overall equilibrium here, but we're doing just the K2 equilibrium, that's why we don't square this one, because in this one, it's not squared. Yeah. So if you were doing the overall one, you would need to square it. But here, because of K2, you can see it's not squared. There's no 2 in front of it or anything like that. So if we do that, that will get us a value for that sort of intermediate of 3.8 times 10 to the minus 9 molar. And now, again, if you want, you can then move to the K1 sort of equation, because we now have just solved for this, and we still know this. So we can now solve for the silver concentration. So I'll do that as well. So if we then use K1 from below, since they gave it to us in this stepwise fashion, we could do this. We're going to take our products over our reactants. And again, since we're doing K1, not the overall, we're going to use the K1 value of 7.4 times 10 to the 8. Rearranging, this would give us silver. Again, these two guys are pretty much just going to switch places. It's going to give us our concentration we just calculated, which is 3.8 times 10 to the minus 9, divided by our 7.4 when it switches places to the 8. And our S2O3, again, because we are using the K1 expression, again, there is no coefficient here, so that's why we did not square it. And if we do that, you will end up with (1.8 to the minus 18). Which is our free silver ion concentration in solution. And it justifies our assumption because our silver concentration should be a very, very small number at equilibrium, which means it definitely is a small number at equilibrium. Any questions on those steps? So here, because it was kind of given to us in a stepwise fashion, we were able to kind of use each of the steps individually, because really each of the steps are equilibrium, which means you can use equilibrium constants that you figured out to calculate it. Just to show you that there's an alternative way, and I'll just show you the one calculation here. When we got to this step here, yeah, so I'm going to actually do that right now to show you, we did calculate this KF, how you could use it and really come up with the same number. So let's talk about how to do that here, just to show you just the one calculation. You could have, again, maybe held off on sort of these calculations here, and you actually could have started with the silver calculation, just like we would have done before. We could have came back and said, we're going to call this X, and use the overall equation and its equilibrium expression. Divided by the silver and divided by the S2O32 minus. Here we would square it because we're dealing with this reaction. And this would equal our K value that we calculated, 2.9 times 10 to the 13. And we could solve for silver first in this case. Using our table numbers would give us 4.29 times 10 to the minus 4 divided by our 2.9 times 10 to the 13 and our 2.86. Again, here we would square it in this case. And if you do that move first, I didn't screw anything up. Always a good chance. Let's see. You get 1.8 times 10 to the minus 18 for the silver, which, as you can see, is the exact same number that we got there. So if you wanted to, you could have used the combined equation. You could have used the KF value and solved for silver. At that point, you then could have, went back into probably this equation here and figured out this guy's concentration as well. So again, there's a couple different ways you could solve it. If you sort of do it correctly, it should all sort of end up in the same sort of number and stuff like that. So any questions on that? So again, you could use the combined reaction like we did previously, solve for the silver ion concentration first. You can see you get the same number, and then go into one of the equations below to find the last one that we were missing. Any questions on that particular one there? Okay, so let's talk about then one last sort of example here of KF and sort of how it can tie together with another K value. So here we want to actually calculate the molar solubility of silver chloride in a 1 molar solution of ammonia. So we have a KSP and we have a KF value here. And we're really looking for sort of the overall reaction that's happening when silver chloride and ammonia get together. So let's take a look at this together to see how this one is a little bit different as well. So if we take both of these reactions and add them together, our silver ion is going to cancel out, and that's going to leave us silver chloride plus ammonia will give us our complex ion plus some chloride. Now, this is a KSP and this is a KF. Doesn't matter that they are different in the sense of KSP and KF. If you remember, we talked about the idea that they're all really K values. It doesn't really matter to the label Ka, Kb, Kc, Kp. They're really all just K values in equilibrium sort of expressions. So although we did add both of these together, we would still do the same thing. The K value here would equal our KSP times our KF. Again, doesn't make a difference that they're technically two different K values, because ultimately they are all still an equilibrium constant. So if we multiply those guys together, we end up with a K value for this overall reaction of 2.4 to the minus 3. So again, we sort of did very similar to what we did before. We added both reactions together, which means in terms of the K value, we do need to multiply them. And again, it does not matter in this case that they're actually sort of different, if you want, in quotes, KSP and KF. We are also looking for something slightly different in this problem as well. We're looking for the molar solubility. So this is really more of a KSP type of problem and how you're going to approach it, because again, we're looking for that molar solubility. The only number that we have is we're starting with 1 molar ammonia. So we will do our ice table here. This is going to be 1 molar as we have from the problem, 0 and 0. We're going to do our plus 2s, our plus s, and our plus s, right, which is our molar solubility. And at equilibrium, we will get 1 plus 2s, s, and s. Any question on that table? Again, since we're looking for the molar solubility, we're going to kind of do it like a KSP type of problem. Our K value for this, our expression, is going to be our products over our reactant. And don't forget, there is a 2 in front of that, NH3, so we do need to square it. It's going to equal our combined K value of 2.4 times 10 to the minus 3. If we put our values in, that is S times S divided by 1 plus 2S squared equals 2.4 times 10 to the minus 3. We do want to solve for S here. Hopefully you could recognize if you look at that, that is a perfect square on both sides. You can take a big square root on this side, a big square root on that side. And that's going to give us S over 1 plus 2S equals the square root of 2.4 to the minus 3. And that's going to give us 4.90 times 10 to the minus 2. We're going to multiply the bottom to the other side. And if we do, we get S is equal to 4.9 times 10 to the minus 2 plus 9.8 to the minus 2S. We want to combine our S's to one side. Gets us 0.902S equals 4.9 times 10 to the minus 2. We want to divide by S to the other side. So that's going to get us 0.054 as the molar solubility of silver chloride in ammonia. So it's the same idea. It was plus 2S here on the table because, again, we're assuming that this reaction is going to head in this direction. Since, again, really the only thing that we had was, I'm sorry, that should be minus. Thank you very much. That's some bad math there. Thank you. Let me refix that. Had the plus in my head there. Thank you. That should be minus. So let me fix some of that there. Sorry about that. So we'll just recalc real quick. Thank you. So yeah, it definitely should be minus 2x in that case. So let's just do a quick recalc here. All right, so this should be minus, that should be minus, which means, again, we should have S is equal to our 4.9 times 10 to the minus 2. This should be minus now. (0.098S). We should add that actually to the other side. Gets us 1.098S equals 4.90 times 10 to the minus 2. And now we should end up with an S of 0.045. Thank you very much. So that should be the molar solubility. It should be minus S here, and again, should be minus S here. And so that looks a little better, I think. Yeah. All right, other questions on that there? So what this shows you is the molar solubility of silver chloride in ammonia. In this case, once we get the right calculation down there, is 0.045 molar. Just for comparison purposes, I think I have it on this one. The molar solubility of silver chloride in water is 1.3 times 10 to the minus 5. And then what we just calculated there was 0.045 molar. So you can see it is much, much more soluble. in the ammonia. And that is because when we talk about KF values, the numbers are so large that when they have the opportunity to come together to make that complex ion, because the KF values are so large, they want to do that. In fact, if you had some silver chloride in a test tube or something like that, and you added some solid silver chloride and you added some ammonia to it, you would actually see the silver chloride disappear, because the attraction of the silver ions to the chloride versus the ammonia is much, much stronger because of that KF value. So it will go from a solid silver chloride to that silver and ammonia complex ion, and it will become aqueous. So you could actually see solid silver chloride sort of disappear. It really doesn't disappear. It just gets trapped in this complex ion because that KF value is so large. And you can see by the calculation here, once we sort of fixed it, that it is much, much more soluble in something like ammonia than water. And water, you're looking at this in terms of solubility, right? So much, much less going to be soluble per mole per liter. Question on that type of calculation. And again, just to go back here. Again, thank you for the minus. Again, it should be a minus, so make sure you correct that. And here again, this is solid, although this is really what we're looking at here. Again, I didn't put any numbers here, so I didn't try to use them anywhere. But as we talked about before, essentially when you do calculate for S, that is really the molar solubility, kind of the whole thing that we're talking about. So that will allow you to kind of relate it back to the silver chloride. And here is that table that you can find in your book, which you might need to look at in terms of KF values. And what we see is when you look at these KF values, pretty much they're very, very, very large, as you can see here in numbers. And again, what that really shows is like that last calculation, that if it's possible to form a complex ion, it's probably going to be very much favored because of that very high K value. Those metals and those ligands do want to come together to form that complex ion. Any questions on KF or how to calculate it or anything like that? Okay, this should wrap chapter 15, I believe. That means, as we talked about last week, and as I put an announcement out, the next exam, which will cover chapters 14 and 15. So usually the hardest exam there, test, titrations, buffers, KSP, KF, will be 1 week from today on next Tuesday. And we'll take it during lab time like we've done previously. Starting today in lab, we're going to do the titration experiment, so it'll be up there for you to do. I am going to talk about it at the beginning, sort of go through some of the ideas behind it and maybe some of a little bit of the calculation ideas. So we're going to talk about sort of titrations and a titration experiment up front here in lab as soon as we take a break, and we'll restart it. And then you could go off and work on that. And obviously you still have the buffer experiment. Reminder that there are some calculation sort of points where you need to kind of get approved before you can kind of continue on and finish the buffer experiment, which is due at the end of the week. I think I moved it to Sunday, maybe. I'm going to move it further to Sunday or something like that to give you a little extra time. But again, you should be working on that. You could start working as well on the titration experiment. And that titration experiment will probably be due in a couple of weeks, I think. It'll give you enough time to kind of make sure you could get through it all. Technically, we'll be doing it all this week and next week, so it'll probably be due maybe 2 weeks from now or so. So that should give you time, but I'm going to open it up today after we talk about it in lab, and that way you could obviously be working on that. And then for the rest of the lab period after we're done talking, I'll be around if you have any questions or anything like that you want to ask about either of those experiments. All right, any questions on any of that stuff before we knock it off for lecture here today? I know we went a little bit long, so we'll start lab around 11:40, I think. Yeah, so we'll start lab about 11:40, and make sure you come in through the lab invitation. All right, I'll see everybody in a bit. We're going to talk about that titration experiment.